Oh, well, thank you for all turning out to listen to a very ancient clodhopper like me. Um, so I'm talking about a new data set, really, we've got from the Falkland Islands. So it's not, it's sort of under review at the minute. So it hasn't actually been published. So you're getting a bit of a preview. Mind you, it's struck a few problems in review so far. So it's in with the Geological Bulletin of Geological Society of America, and we've had one or two rogue reviewers who are not very attracted to the position we're putting. So I'll see if I can persuade you to the position I want I want to present. So it's a joint project, and I've been to one locality in the Falkland Isles on a cruise ship, and I've been to Port Stanley, and I picked up two or three samples, one of which I processed. All the other samples were picked up by a colleague called Eric Roberts, who's been to the Falklands about 3 times, and he didn't get himself blown up. There are mines all over the Falklands left over from the war, and the penguins are too small to set them off, but apparently people aren't. So he survived and collected a bunch of samples, and I think I did most of the work on the samples, and I've written the interpretation. Took a while to get Eric on board because he's South African, and he liked the South African connection for the Falklands because he'd seen the rocks and he was a bit committed to that mentally. But eventually I got him round. So the Falklands are down here. What are we? Down here. And they're about 800 kilometres away from South America. And the red spots, as you can see on there, are other bits of real estate poking out of the ocean. They're all volcanic bits and pieces. But the Falklands is all sedimentary. Darwin visited there, when Darwin was getting around in his exploration, and he collected fossils from the Falklands. So, knowing that it was a sedimentary bunch of rocks there has actually been known for a very long time. So, there are the Falklands. The rocks are actually very well exposed because as you can see, there's a multitude of coastline. The relief goes up to 500 or 600 metres, and there really is a lot of outcrop. So the geology has been done in great detail by a couple of people called Aldous and Edwards, who come from the Geological Survey of the UK, of course, and the UK still owns the Falklands as a result of the war with Argentina. So they've mapped the Falklands in great detail. So they've set up really the geological foundation for everybody's future work. So the Falklands, how did they get to where they are now? Okay, and this is that's on the left here is where they are now. Okay, and you can see they're sort of connected. The lighter yellow here is continental crust. So the Falklands are connected with submerged continental crust to South America. So it looks as though it's a bit of South American real estate, really, when you look at that. And on the right-hand side, there's a reconstruction done by a couple of publishers pretty recently, 4 or 5 years ago, using G plates, and puts the Falklands where you can see here, a bit south of South America, of South Africa rather. But as you'll see, there's a great enthusiasm in the literature, but not putting the Falkland Isles here, but putting them up here, where the Morris Ewing Bank shown on this particular diagram. So that's where G-Plates puts it. But as I say, there's great enthusiasm for putting it up here. So what's the basis of that enthusiasm? Well, the enthusiasm is this. When you look at, there are two major rock systems on the Falklands and on Southeast Africa. There's the Cape Fold Belt and there's the Karoo Basin. And there are equivalent rocks on the Falklands, but what you have to do to get it to match up, you have to spin the Falklands 180 degrees, okay, to get it to match up, as you can see there. So that the Cape Fold Belt is equivalent to these rocks around here, which I'll get to in a minute, and the Karoo Basin connects to this bit that's orange in here. So to do it, you've got to get Stanley, which is there, to Stanley, which is here, which involves a 180-degree rotation. Now, by any geological venture, that is a big ask, but it's a very popular view in the literature. And that's why I think we've struck a bit of problems in trying to put arguments that counter that proposition. So this is where people want to put it, okay? And the black there is glacial diamictite, which is late Carboniferous, early Permian, both on the Falklands and in South Africa. And you can see you can get them to align, and if you do that, you get the older rocks underneath the diamictite to line up, and the younger rocks above the diamictite, which are part of the Karoo Basin, to line up as well. And you can fiddle around with current directions as well, and you can make them line up pretty well. And we know both the rocks in the Falklands are pretty lightly deformed. The Cape Basin, south of the diamictites, is rather more deformed in South Africa, and you can look at the divergence relationships, and the rocks in South Africa are merging north, and if you spin the Falklands, you can get the structure there to verge north as well. Okay, so it's all looking pretty good at the minute for the proposition. And then you look in detail, right, at the infill of the Karoo Basin with the younger part, the Permian part of the stratigraphy in the Falklands. Okay, and it's in what's called the Eka group in South Africa. The Dwight is the glacials. Okay, here are the glacials in the Falklands. And we're looking at the Eka group in South Africa, and a bunch of formations in the Falklands that are thought to be comparable. And indeed, when you look at the lithostratigraphy in a bit of detail, there's a pretty good comparison between the units in South Africa, and Eka Pass is on the eastern side of the Karoo Basin. So this is how things are supposed to be matched up. And people would think, well, actually, what's on the Falklands is actually just a bit of the Karoo Basin, which has been transposed to the other side of the Atlantic. Okay, and spun 180 degrees. That's the general idea, and people are persuaded because the match this part of the succession is pretty good. Okay, so it's the Lafonia group in the Falklands and the Eka group and rocks above in South Africa. So that's compelling evidence for a lot of people for the match, that the stratigraphy matches up. Okay, and here's there are mainly just open folds of the rocks on the Falklands. The structure is not too complicated, but you can get if you spin it, you can get a northerly vergence. Otherwise, it's verging, as you can see here, to the southwest. Okay, spin it, and you get it going north-northeast, which gets it to fit with what you see in South Africa in the older rocks. Okay, yeah. So now this is a bit of a clincher that got published quite a while ago. It's in the late 80s, so what's that, 25 years ago, 35 years ago. There are a bunch of basic dikes in the Falklands. They're shown here in red. Okay, and they've been subject to the paleo magicians have got in here, and they've collected about 14 dikes samples, and they've done what paleo magicians do, and they worked out that the Falklands don't actually fit on the apparent polar wander path for South America, and they're a better fit with what was thought to be happening with South Africa. So this is compelling evidence, but there's a bit of a snag because the dikes are of various ages. There's a Jurassic lot, which these people thought they were analysing, but they didn't do dating, so don't know. They only thought there were Jurassic dikes then, but it turns out there are Cretaceous dikes as well. So it's a little bit uncertain whether they got all Jurassic or mostly Jurassic and some Cretaceous, or just what happened. And in addition, people have debated the veracity of their findings. So that's under question a bit. Okay, so here's the evidence supporting rotation. There's a paleomag, there's the Permian stratigraphic sequence that we've just talked about, there's the structural vergence, which you can get to match up if you spin it, and you can get the paleo current directions a bit to align as well. So that's the evidence for the story. So here we go. This was supposed to happen in the Jurassic. Okay, so here's the Falklands starting off a bit further north than what's shown here. Okay, so the Falklands would have been sitting up here. You open up a little bit of ocean floor in there in the Jurassic, which is genuine because there's a sedimentary basin. The East Falklands, what's now the East Falklands Sedimentary Basin, which opened up in the Jurassic. Well, that's the interpretation of what's known of the seafloor underneath it. So close it up, and you get the Falklands back up here. Oh, good. And then you spin it. All right, here we go. All right. So so it starts here, and you spin it around to there, and you can get it a bit further round if you play your cards right with the opening of the Atlantic. You can get it to a proper upside down cake. But you look at that and you say, well, what's actually the mechanism of doing that? Because you're in continental crust and you've taken a portion of continental crust and you've spun it and you've moved it a significant distance. So, you'd have to have a massive shear zone to do that. And if you look at how people interpret this Falkland Islands microplate, it's oblong. So, if it was round, it'd go a bit more rolling a log. But oblong, it just increases the difficulty to do that. So there's no mechanism really, the useful mechanism that anybody's proposed to achieve this rotation. So, but as I say, it's a very popular story in the literature, and there's a slight overlay of politics in a way, because the British would be keen to have this. They'd be keen to have the Falklands originally as part of South Africa and not part of South America and attached to Argentina for reasons I don't really have to explain. Okay, so a little bit of politics. So the mechanism is not known. And in addition, there's particularly to the north and also to the east of the Falklands, there are sedimentary basins which are shown here in the orange, the stuff. This is the North Falklands Basin. Now, part of the reason why the Poms wanted the Falklands is because of these sedimentary basins, because they were thinking that these had hydrocarbons. So they've been pretty well investigated. They've been drilled and looked at quite extensively seismically. So this is a cross-section of this North Falklands Basin up here. This is the Jurassic, is the blue, and there's still older sediments underneath that, which at least in this basin here goes down into the Triassic. And you look at that and you say, well, how is this sequence actually going to form here while the spin was going? Wouldn't there be some disruption in these basins? Wouldn't you see some disruption if you got the spin on going in the Jurassic? So you're just on that evidence alone. The spin story is looking a bit dicey. Now, here's the sequence in the Falklands. There are the rocks that you can see as mapped by the folks from the Geological Survey in the UK. And there are two groups. There's this West Falklands group, which is pretty much all there is on West Falklands. And then there's this Lafonia group, which is quite a bit thicker and represented on what is now the southern part of East Falkland. Okay, and it's a pretty substantial succession, as you can see. So this West Falkland's about 4 k's thick, and this Lafonia group's pushing 8. So it's a big heap of sediments you've got here. So the glacials that I was talking about are down here. That's where the glacials are, and this West Falklands group sits underneath the glacials, and the West Falklands go from Devonian down to Silurian in age, and I'll explain the dating in a minute. So here's the Fitzroy Tillite, and there's this pretty thin Port Sussex formation, and my mate Eric has got a very good eye for picking out ash beds in sedimentary sequence. He's got a really good eye for it. And lo and behold, he found some ash beds in this Port Sussex formation. So ash beds, zircon from the ash beds, date the ash beds, date the Port Sussex formation. Okay, is how you go. And the result standard stuff. Right, we've got reasonably good dates out of these tuffs, and then you put the dates on the stratigraphic sequence from South Africa, which is shown here on the left. They've got tuffs too, which are dated, and you put our new Falklands data on the Falklands column to the right, and you can see that the Falkland dates are younger than the dates of what are supposed to be equivalent units in South Africa. So the match isn't there. They don't correlate. I mean, the rocks look similar, but the ages don't match up. So it's not a good story. And so now, much of the Falkland succession is this West Falklands group is pre-Permian age, and how does it match up to its equivalent in South Africa? I've only talked about the Permian so far, so let's see how that goes. And the answer is not too well. The match isn't very good, and so the total thickness of the sequence South Africa, its structural complications, the contemporaneous units. You can see there's a lot of subdivision here in South Africa for the sequence. Subgroups with formations inside. All these formations down here not much in the Falklands. Now, both of these sequences actually bottom onto basement. So there's not as if there's anything missing from the Falklands. These should be comparable. And actually, the match is far from great. Okay, so you can argue your case for the spin on the Permian. It's a lot harder to argue the case for the spin on the older rocks. Okay, okay, and the answer is not well. Yeah, this is a match of the older rocks, South Africa to the Falklands, age difference, thickness and lithologies, deformation and metamorphism. None of that matches up too well. Okay, so you can argue your case for the Permian, but you're not going to get much mileage out of arguing the case of the Cape Basin with the older rocks in Falkland. So the conclusion I'm led to is that no, the Falklands are not part of the Karoo Basin, and they're there where G-Plates actually puts them, this reconstruction, and they're a discrete basinal entity themselves. Yes, there's a comparable sequence with what we see in South Africa, but it's a different basin accumulation and deformation. The divergence directions, I'd argue, don't mean anything because inversion of the basins just produced a different result from what we see in South Africa and what we see in the Falklands. Okay, now we've collected sandstone. Well, I've collected one. Okay, Eric collected the rest. So we've got these sandstone samples collected from. I've been talking about the stuff down here, but we've collected stuff through the sequence. Not much I'd have to say from the West Falklands group, but there's a pre-existing literature on zircon ages from the West Falklands, so there's quite a bit of data there to inspect. But we've got the first lot of data really on the Lithonia group, which is over here. The first lot of detrital zircon age data out of that. Okay, so what's that look like when we get it together? Well, there are two age spectra. Okay, so most of the Permian, not quite the base of the Permian. So this is the very base of the Permian down here. Okay, but all the stuff up here has got this sort of pattern. And you can see there's a very prominent cluster, and you won't be able to read from where you're sitting what the number is, but that's Permian. Okay, so there's a detrital zircon cluster, which is pretty much the age of the rocks. And we know the age of the rocks a bit because there are Glossopteris plant fossils in the upper part in particular. So we've got fossil evidence that it's Permian, and we've got the ages, our ash ages down here, which are Permian as well. Okay, so the sequence is all Permian, and so we've got this big Permian cluster up here, and you look at that and you say to yourself, well, that's got to come off a magmatic system to get that cluster of Permian zircon. It's got to come off a magmatic system that produced the sediment that went into producing the Lithonia group. Okay, this group. Now, the West Falklands and the very bottom of the Lithonia group have actually got a completely different profile. Okay, a bit of Permian right at the bottom here, but the rest of it, all of this, and this is our data, but there's a lot of other data. They all show this. So there's a prominent peak. You could almost be in Australia when you look at this distribution. So you've got a prominent peak that's sort of 500 to 600, and there's another prominent peak here, which is sort of 950 to 1100 million years. Okay, and the important thing to notice is that the Fitzroy The glacial deposit down here has got exactly the same profile as the rocks here in the detrital zircon. So you look at that and you say, oh, well, you know, they all share some sort of a provenance connection. I wonder what that provenance connection might actually be. Now, it turns out, here's the Falklands in this reconstruction, which is, you know, I wouldn't argue too much with this, but there are sedimentary systems equivalent to the older part of the Falkland succession, which extend right across East Antarctica into South Africa and across into sedimentary basins that are formed here in Argentina. And so the question is, how do those zircon age profiles actually match up with the record that goes across here? Okay, how does it match up? And the answer is, ooh, actually pretty good. So this is color-coded. Falklands data, ours and other people's in black. This is South America. This is South Africa. Very big data set though. And this is Antarctica up the top. Okay, so right along that belt of equivalent sedimentary units across East Antarctica, into South Africa, into the Falklands, across into Argentina. Oh, it's all got the same profile. It all looks the same, right? And what's more, here's the diamictite. This is the Fitzroy-Tillite, okay? And, you know, it's a match. So all of these rocks were derived from some, you know, parentage, some source terrain that produced this profile. And the Fitzroy-Tillite shares that profile. It's the same profile. So it all came, where it came from, it's all in common. Now, this is recently published a couple of years ago. It was only a year ago. Maybe it's only a year ago, where people were very keen to get the older sequence in the Falklands and the stuff I've just been talking about on the previous slide from the interior of South Africa. Okay, all coming down from up here in South Africa, all coming from the north and maybe a bit coming from the east out of South Africa, out of Antarctica, and into the Falklands. So that's the idea. But there are a few. Well, there's a major problem with that interpretation because there's no real source for that prominent 500 to 600 age peak I showed you on the previous slide. You can't get that out of South Africa. It's actually not really there. You know, you can find a couple of pocket handkerchiefs of rock that might actually fit that age profile, but nothing substantial. And what's even worse, you've got this dark green here. That's Archean crust. So you'd think, you know, if you've got the Falklands here and the Cape Basin here, you would, and getting sediment from up here, you'd think you'd get a bunch of Archean grains in there because there's a big Archean terrain which is so proximal to where you are. So, but you look at the detrital zircon age profiles, there's almost no Archean. It's vanishingly, there's, you know, across the whole data set there might be 10 grains. Okay, so it doesn't stack up very well. Okay, now it gets worse. Remember, I was saying that the tillite in the Falklands and elsewhere has got the same detrital zircon age profile as the rocks beneath it, matching up perfectly well. And there's a bit of extra data for the diamictites. Okay, so some of them. So these are sequences that have been documented from Argentina and southern Brazil. This one's from South Africa. The red are ashes. Ashes. So where are we going to get those ashes from? From the interior of of Gondwana, right? It's going to be quite a bit of an ask to get that. Furthermore, there are some limestone clasts in a lot of these diamictite sequences that have got fossils. They've got archaeocyanid fossils, and you can't get those from the interior of Gondwana either. Okay, so where are we going to get this stuff from? Well, the answer is, I think, pretty obvious. We're going to get it out of the Ross Origin. And the Ross Origin runs across East Antarctica and West Antarctica even more. Okay, and it's an orogenic system that went through, it's equivalent to the Delamerian in Australia. So it went through to the Cambrian, okay, and what sort of ages have we got for its igneous connections? It's looking pretty good. About 500, going back towards 600. Okay, and there's a lot of data, and the blue one here is a flooded shelf with a bit of carbonate platform and producing the archaeocyanids that we can see in the diamictites. So the diamictites clearly have a connection to the Ross Origin, okay, not to the interior of Gondwana, but the diamictites have the same detrital zircon pattern as the older rock. They're all in it together. Okay, so well, the red there is the ages from Antarctica, and you can see they're extending back towards 600, and they go up to 480 or so. So there's a lot of igneous rock from which we can get the zircon population we see in the older Falkland rocks and equivalent sequences elsewhere. And there's detrital zircon in the sedimentary sequences out of the Ross as well. And that's what we can see up here at the top, the stuff up here. And, this looks familiar, doesn't it? You can't read the numbers, you can here. Okay, there's the 5 to 600. Here's the 950 to 1100. So, it's the same zircon population, age population we're seeing in those older sediments on the Falklands. So, to my mind, it's pretty clear where all of those sediments came from. The older Falklands rocks, right up to the diamictites, they came from the Ross Origin. Okay. And of course, nobody argues that there was an active margin that produced the later Permian stuff everywhere, including the Falklands and including in the sequences running across Antarctica, South Africa, South America. There are ashes just about everywhere, and we've got this detrital zircon spectrum. So F and G on here, that's the Falklands result. Below that is South America. Above that is South America and Antarctica, and you can see it's a matching pattern, but for the entire region under discussion. So everybody's happy with this pattern here. Okay, active margin, active margin, igneous activity producing detritus, which is going into these sedimentary basins. Okay, so here's a general conclusion at this point. The Falkland succession and southern Gondwana correlatives accumulated in the context of an active margin back arc setting of long duration, spanning much of the Paleozoic. Two sequential basin systems are involved. The first ending with deposition of the Fitzroy Tillite, and the second Permian and Triassic. Okay, and they've got different zircon age profiles in the sediments, but they both came from the Ross origin and its successor. Okay, successor system. Okay, so we can plot up now the basinal succession. Okay, so this is Argentina. This is southern Brazil. Okay, this is this is a bit further north, but this is South Africa. This is the Falklands. This is the Ellsworth block, which is on the end of East Antarctica. And here's the Transantarctic Mountains, right? Here's the Permian sequence. They all got the stuff with the diagonal lines is the diamictites, okay, which match all the way across. And there's quite a lot of age dating because these little dots here show sort of maximum depositional ages for the red dots, but these other symbols up here show ashes. Okay, so it's pretty well controlled. Not so much when you get into Victoria land. Okay, so that's the younger sequence, and it's Permian just nipping into the top of the Carboniferous, and there's the older sequence down here. There's an unconformity underneath the diamictite all the way across. Okay, and here's the older sequence for the Falklands. Here goes down into the Silurian. We know it can't be older than Silurian because it bottoms on basement, and the basement's got Silurian dikes in it. Okay, so the cover it's got to be no older than Silurian. Okay, so there's a bit of age control. The best age control here is in the Devonian. Just about a lot of places actually got fossils of Devonian age. Okay, and then there are maximum depositional ages as well across here, and some of the Antarctic sequences like this Ellsworth block might actually go back as old as late Cambrian. Some of the others go back into the Ordovician. All of them got the Silurian, and all of them got the Devonian. Okay, so what sort of a picture do we end up with? Well, here's the picture. Okay, Silurian, Devonian, the older rocks. In my estimation, we've got a super basin which runs across for amazingly, about 5,000 kilometres, a monumental distance. The green are the bits we know about. The yellow is supposition, but I think that's a super basin, and we just looked at the stratigraphy before that relates to these green bits. Okay, and I'm arguing here's the Ross origin out here. Okay, and it's got granitoids scattered along it in bits and pieces, which will produce the material of the right age. It's got detrital zircon out of this system, which will produce detrital zircon of the right age in this age, this sedimentary system over here. So this sedimentary system wound through at least the Silurian, the Devonian, a bit older than that in places. And then there was a break. Nothing happened everywhere, unconformity everywhere. And we're into the Permian. Here's the Permian system here. And it's a repeat, just younger. Okay, stacked on top of this sedimentary system here. So I'd argue there are two super basins, right, sitting on top of one another, both actually fed from an active margin out here, the Ross, and its successor system out here. Pretty good evidence of Permian action for the successor system. Lot of igneous rocks in South America and scattered along in West Antarctica as well. Okay, and so I'd argue that there's been amazingly consistent plate engagement along this 5,000, 6,000 kilometre stretch. Okay, and with that the plate engagement, the consistency of it produced consequential, consistent inboard subsidence and basinal development right along the stretch in two superbasin systems. So that's the story, generally. So I just hope I can get it published. Well, most of you stayed awake for at least part of it. At least part of it.
Thank you. Does anyone have questions for Bob?
Yes. Yes.
Really well presented. I've never had any interest in the Falklands, and I'm intrigued by it. I am doing a lot of age dating where I'm working right now. In fact, I've just smuggled a few samples back to send you into codes. How many age dating samples in total have you accumulated?
Process. For the lower part of the succession, underneath the diamictite, our data and other people's data, there'd be probably 15 samples, that order. And for the stuff that we've only us have done the stuff above the diamictite, and we've got about a dozen samples.
Okay. Yeah. Good. Okay. That's thanks.
All good.
Any other questions?
Yeah, Bob, the most of those basins outcrop pretty well in East Antarctica, and yet the Falklands Plateau seems to be attached to South America and has followed it across the Atlantic Ocean. Why is there only a small amount of outcrop in the Falklands? What happened to the rest of the basin? Is it sitting underneath?
Oh, well, it's submerged, you'd argue. I mean, it bottoms onto basement on West Falkland, so you can actually see the unconformity at the base of it on West Falkland, but you don't know where the top is. It's just goes, it's still going up when you hit the sea.
The unconformable gap between A and B is how long?
Just happened here. Yeah. Well, it's the spots you can see are the age control. Okay, and so it's reckoned that the diamictite. It reckons the diamictite is actually registering a climatic event, which was pretty universal. So everybody thinks the diamictite. So responding to that climatic event that produced the glacial deposits. And so there's a little bit of dating, as you can see, in the diamictite, in the Karoo, and in this Kalahari Basin. Okay, but that's the age control, these spots that you can see. And the age control is not so good in the solar sequence. It's not so bad in the Devonian because we've got the marine fossils in some of the sequences.
The unconformable gap. What happened?
Well, I guess subsidence for whatever reason stopped. So whatever the plate engagement driving subsidence was doing, it sort of did something else for a period of time and didn't actually sponsor subsidence. You'd have to argue, because if it kept on sponsoring subsidence, then infill would have continued. Yeah. Now there was no, don't think so. Now there is a genuine unconformity at the bottom of the diamictites that you can see it in the Falklands and you can see it in other places as well. So it's the time break is actually supported by that unconformity. So it's all pretty fucking. So the problem I'm having in getting this reviewed is that it's going, of course, to reviewers who are very keen on the rotational hypothesis, and so they're not keen on having that shot down.
This type of dating?
No, that needs to be done, and that's generally agreed in the literature that needs to be revisited. Yeah.
Any other questions from the floor?
But you've got to be a firm believer in paleomag, and Yeah, I'm not a great believer in paleomag for some evidence. Laurie might remember this, is the Theresa Creek volcanics in Queensland, undated. So the paleomagicians got in there, worked their system, plotted it up on an apparent polar wander path, got an age, and then somebody dated the Theresa Creek volcanics. Guess what? I don't have to tell you the answer.
Any other questions for Bob? Geez, that's it, Bob.
Well, thank you.
You've learned. Thank you very much.
Yeah, you're an attentive, mostly an attentive audience. I did see a few lids drop occasionally. I tried to speak up and, send a bomb out, but yeah. All good. All good. So cheers. So thanks for turning up and listening to an old fella rambling on about a part of the world you've never been to.